All right, so along we've been talking about functions and been talking about some generalizations of functions. Now we want to move into specific functions. The first of which is going to be the linear function, which of course is just a function whose graph is a line, specifically a non-vertical line, because then it wouldn't be a function. So linear functions are going to have the equation of a line, and since it's written isolating the y or the f of x is going to be in the slope-intercept form of the line. So everything we're going to do is going to have an equation resembling the slope-intercept form for the equation of a line. Okay, so let's start off with a couple problems, the likes of which you'll see. So we'll say we'll work with an assumption that the function fx is linear, which means again it's going to be of this form, mx plus b. And f of 4 is negative 4. That means the function evaluated at 4 is negative 4. Also, the function evaluated at negative 6 is negative 9. So we want to find the function. Well, this is essentially giving us points because when we plug in 4, we get out negative 4. When we plug in negative 6, we get out negative 9. So this notation here is nothing different than saying, oh, here's a point 4, negative 4, negative 6, negative 9. What's the equation of the line going through them? So we'll proceed with it as we would in that instance, in which case we find the slope, easy enough, difference in the y's over differences in the x's. Slope reveals itself to be 1/2. Okay, then we'll go to our point slope form, or the modified point slope form, and find the equation of the line, and we're done. Of course, we are expressing this as a function, so we'll call it f of x equals 1/2 x minus 6. So again, no different than finding the equation of a line given 2 points. The 2 points a little bit in disguise. F of 4 is negative 4, f of negative 6 is negative 9. Let's proceed with a couple other examples. Okay. Again, we have to be of the assumption that what we're doing with is linear functions. This is saying here's some linear function. The function evaluated at 4 is negative 5, so again it contains a point 4, negative 5. But now this says the inverse of the function evaluated at 3 gives us 0. Okay, so we're asked to find from there to find the function and its inverse. Okay, so here's the thing. We know that 4, negative 5 is on the function. We also know that 3, 0 is on the inverse of the function. So with 3 zeros on the inverse of the function, then the function contains 0, 3. So we work off of that. So again, this notation, 4, negative 5 is on the function, 3, 0 is on the inverse, or 0, 3 is on the function. So we're right back to where we were with the previous problem. Find the equation of the line given these 2 points. This is going to be simplified by the fact that one of the points is, of course, the y-intercept of 3. So compute the slope. Slope ends up being negative 2. Y-intercept is 3. We have the equation. Okay, not so difficult. Now, what's the inverse? Well, you could do a number of things. You could come back here and you could do the same thing because you know the inverse contains 3, 0, but you also know the inverse contains negative 5, 4. So you could proceed with it off of those 2 points. You could come down here, call this y, exchange the x and y, solve for the new y, or you could remember what was shown in general, and maybe you want to just show this. If y equals mx plus b, then the inverse is going to be 1 over m times x minus b over m. I suggest that you work that out for yourself to see. Okay, and then using that format, we can just throw in the values, and here we have the inverse function. Okay, now we're going to look at some practical examples of the inverse function of the linear function. So here's a depreciation model. Okay, a new car was bought for $22,500. We're assuming that it has linear depreciation. That is, with every passing year, it goes down. Okay, there's an expression, a function that we're going to find for this. Okay, we're going to call v of t. The value is a function of time, if you will. Okay, we know at when you first bought it was 22.5. 3 years later, it's down to 17,750. So a couple questions to be asked. Okay, what is the value of the car after 5 years or 10 years? Okay, and how many years will the car be worthless? Have no value. Of course, these can only be answered once we find the value as a function of time. Okay, the VT uh, linear model for this. Okay, so really it's no different than what you've seen in the previous slides. Okay, these are essentially points. Okay, um, if we call the time when we start t equals 0, when you first bought it, that's the time t equals 0. The value of the car was 22.5, so that's essentially one coordinate. Okay, v of 0 is 2250, 22,500, which is the point 0, comma 22,500. 3 years later, okay, it's worth 17,750, so v of 3 is 17,750. So again, these are 2 points. The 2 points are 0, 22,500, and 3, 17,750. So again, the problem is nothing more than finding the equation of the line going through those 2 points, whereas those 2 points were a result of the evaluation of the function at time t equals 0 and t equals 3. So we'll get the function from these 2 points, and then we'll come back and answer these questions. Okay, so easy enough to compute the slope. Okay, the slope is going to be negative because the price of the car is depreciation. That is the slope is 1,583, which means the value of the car is dropping in excess of $1,500 annually. Okay, so the equation, again, y equals mx plus b, or in this case, vt equals mt plus b. Notice our y-intercept point is right here for the picking. Didn't have to do any calculations there. Pretty straightforward. So that's our function. We'll evaluate that function at 5 years, at 10 years, okay, from which we'll find after 5 years the value of the car is at just under 15,000, 14,593. Plugging in 10 into this expression, we get the value of the car in 10 years is $6,600. Then if we want to know when is the car worth nothing, then our v of t here is going to be set equal to 0. So we're going to take this, we're going to set it equal to 0 and solve for the time for when that occurs. Doing that, we'll find that the car is theoretically worth nothing in 14 years, okay, according to this model, this depreciation model. Okay, so now let's talk about another application. We'll talk about a growth population model. Okay, so in this instance, we're going to take some information from the census of from a small town, who says that in the year 2000 the population was 16,583. 10 years later, the population rose to 18,202. So what again is really no different than what we've done before. We're trying to find a model that mimics this the population growth for this town. So we're going to say, assuming linear appreciation, predict what the population is going to be in 2020, 2015, or go backwards and find out what the population would be in 1990 or 2005. Okay, so again, once we get the model, since it's linear, it is of the form, okay, y equals mx plus b, but since we can name functions in any different form, we're going to call it p of t, where p is for population as a function of time. So p of t, population as a function of time, is the name of our function, and it is going to be of a linear form. And so all we have to do is find 2 points and find the equation of the line through those 2 points. Our information says year 2000 was the first year of the census, so we'll just call that year 0, at which point the population was 16 grand, okay? And then 10 years later, in 2010, we've got 18,000. So here we are, these two data points, year 0, 16,000, year 10, 18,000. Through those 2 points, find the equation of the line that contains them. Again, here, this one nicely is the y-intercept point, so all we have to do is compute the slope. The slope is easily enough determined. The difference is in the y divided by 10. So since we're talking about human population, we've got to round this. To the whole number. Okay, actually round it up. 162 is the growth rate. So the population is the rate of change of the population is 162 people annually. So simple enough. Our function will be the population as a function of time is 162 times t, where t is the number of years, plus the y-intercept, 16,583. So we could use this to predict the future population. So the 2020 population will be year 20, since year 2000 was the year 0. So we'll evaluate our P of t. We'll do P of 20, find that population, 19,823. Let's find the population 2015, which would be P of 15, which again, just plugging in 15 into our P of t function gives us 19,000. P of 5, the year 2005, the population is 17,393. And if we're going backwards, then if we wanted to find this population in 1990, so that would be with time -10. Okay, not that time is negative, but for our model, that's 10 years in the past. In which case, if our model serves right, then I'm saying our population is just under 15,000 back then. Okay, so again, these are just mathematical models using the notation of a linear function to try to mathematically model the situation described. Okay, so I hope you find that interesting, and you can tackle the problems that are going to be assigned. Okay, all right, and we'll stop it here. And not with that, we'll stop it here with this.